Welcome to the first online lecture for Math 2610, Linear Algebra. We'll be looking at section 4.1 out of the book in this lecture. Okay, so let's start by looking at a set of vectors. So I am looking at a set of vectors that satisfy this. So all of the vectors in R3 that satisfy this equation, where 2 times the first component minus the second component plus the third component equals 0. So all of the vectors that satisfy that. So, for example, the 0 vector, that satisfies it. The vector 1, 2, 0. You plug those numbers in, it equals 0. So that vector is in the set. 3 minus 1 minus 7. That vector is in the set. Okay, so that's examples. I'm looking at all of the vectors that satisfy this condition. And now we're going to look at a couple of properties of the vectors in this set. The first one, we're going to look first at something called additive closure. So again, here's my set, the same set. Now, I have two vectors, u and v, and I tell you that those vectors are in there. What does that mean? Well, that means that for those two vectors, it satisfies that equation, and the second vector satisfies that equation. That's the definition of being in the set. Okay. So u and v are in there. And now I'm going to say, what happens if I add them together? What's going to happen? Well, when I add them together, I just get a third vector. Okay, so if I take those two, any of those two examples or any other two vectors in there and add them together, I get a new vector. That vector is u plus v. So I've just added them together. What is u plus v? Well, when you add vectors, you just add the components. So that's what it looks like. That's what u plus v looks like. Now, my question is this in the set or is it out of the set? In other words, does it satisfy that simple little equation? So what do? I take the three components of that vector, put them in that equation. So 2 times the first component minus the second plus the third. And now I take it and rearrange it a little bit. So rewrite the equation, what I have here a little bit, and I get this plus this. But if I look at those two parts from above, that's equal to 0, and that's equal to 0. So 0 plus 0 equals 0. So for my new vector, when I plug it into that little equation, I get that it's equal to 0. That means that it's in the set. So my new vector, u plus v, is also in my set. What's this telling me? It's telling me that if I have any two vectors in the set and I add them up, I can't get out of my set. I stay in there. I'm always in there. So I don't move out of it. Okay? I can't get out of this set that I've defined. So let's look at another property of it. I have my same set, but this time I'm given a vector and I'm given a number, a scalar. So because my vector is in the set, again, it satisfies that equation. But now what happens if I multiply that vector and that number? Well, I get a new vector ku, and it looks like that. When you multiply a number by a vector, you just multiply all the components by that number. So, is this in the set? Well, plug those three components of the vector into the formula, rewrite it a little bit, pull out the k, and you'll notice that that is equal to 0. It's the exact same formula that we had above. And we start out by saying that's equal to 0. So, for the new vector ku, it also satisfies that equation. That's equal to 0. So that means my new vector is also in S. Multiplying by a scalar doesn't let me get out of the set. I stay in the set. This gives me two properties of a set, of this particular set, and these are a couple of the core properties of what is called a subspace. So a subspace is a set that satisfies three properties, actually. The first one is that the 0 vector has to be in it. Well, we started off by giving the 0 vector as an example of something that's in there. So the 0 vector is in the set. The second thing is what's called closure under additive vector addition. So when you have two vectors you start within the set and you add them together, you don't leave the set, you stay in it. So you can't get out of the set by adding things together. The third property is closure under scalar multiplication, and that's the last thing we looked at. When you have an element of the set and you multiply it by a number, you're still in the set. It stays in the set. That's called closure under scalar multiplication. When those three conditions are met, that means that you have a subspace. It's like, remember, a subset is just a group of things that are inside something else. A subspace is a special kind of subset. It's a subspace that satisfies those three properties. Our earlier example does satisfy those three properties. So our earlier example is called a subspace of R3. So, as an example, let's take this. Here's another set that I've defined. And we're asking, is this a subspace of R4? Now it's a subset. It's a bunch of vectors that are inside R4. But is it a subspace? So to see if it's a subspace, you have to answer the three questions. First, is the zero vector in S? Well, is the zero vector in S? Well, using our definition above, if we say let S1 equal 0 and S2 equals 0, those are scalars, then this shows that the zero vector, 0, 0, 0, 0, is in S. It satisfies the definition. Okay, so 0 is in there. First condition, done. Second condition, is it closed under vector addition? So we're going to say, let U be some vector in there, U1, U2, 0, 0, and V be a second vector, V1, V2, 0, 0. What happens when I add them up? When I add them together, U plus V is equal to U1 plus V1, U2 plus V2, 0, 0. Well, it's obvious this is two numbers followed by two zeros. That is in S. So vector addition is satisfied. When you have two vectors that are in your set and you add them together, you're still in your set. You don't leave your set. Third item, scalar multiplication. Again, we let U equal U1, U2, 0, 0, and K be a scalar. Then, what happens when we multiply them together? K times U is equal to KU1, KU2, 0, 0. Those two numbers are scalars, so that is in S. It's easy to see that it is still in our set, so scalar multiplication is defined. So, our set S is a subspace. It satisfies the three conditions. It is a subspace. What about this? What about a set like this? Here it's very similar to what we just did, with the exception that my two numbers, they're greater than or equal to 0. So, is this a subspace? Well, let's just take a look at one example. I'm going to say, let U be 1, 2, 0, 0. Now, it's obvious that that is something that is in my subset, because the first two numbers are greater than or equal to 0. And I'm going to say, let K equal -1. Now what happens when I multiply them together? Then KU is equal to -1, -2, 0, 0, which is not in S, because my first two numbers are not greater than or equal to 0. So this is not closed under scalar multiplication. So S is not closed under scalar multiplication. And S is not a subspace. Okay, so notice when you want to show something is a subspace, you have to show it in general. You have to show it for all possible U's and V's, all possible elements of that subspace, of that subset. When you want to show that it's not a subspace, you just have to have an example. Being a subspace means it works for everything. If it's not a subspace, all you need is one example to show that those conditions don't hold, and you're done. So in this case, all I had to do was find one vector and one number that multiplying them together left the subset. That means it's not a subspace. So a couple of properties about subspaces when we're talking about Rn. First one, Rn is a subspace of itself. Okay, so imagine why. When it comes to those three properties, first property, 0 is in there. Well, 0 is in Rn, the 0 vector. What happens when you have two vectors in Rn and you add them together? You just get another vector in Rn. So it satisfies additive closure. And what about the third one? If you have a vector in Rn and a number, you multiply them together, you just get another vector in Rn. So it is closed under scalar multiplication. So Rn is considered to be a subspace of itself. It's equal, it's the whole thing, but we still say that it is a subspace of itself. The second one is a special subspace called the 0 subspace. Okay, if you take just the 0 vector and think about how this satisfies the three conditions. So if you have just the 0 vector, what happens? Well, does it satisfy the first equation? Is 0 in there? So the 0 vector is definitely in the subset that is only the 0 vector. So trivially, it's there by definition. What about the second one? The second one says if I take any two vectors in there, what happens? And add them together. Well, my first one is the 0 vector, and my second one is the 0 vector. Those are the only ones in there. I have no choice. Then u plus v is just equal to the 0 vector, which is contained in my subspace. I haven't called it S, I've called it 0. Okay, so adding together any two things in there stays in there. There's only one thing in there, but it works. So third condition, u is any vector, which again has to be the 0 vector because it's the only one. K scalar, then k times u. What's that equal to? No matter what k is, you end up with the 0 vector again. And that is in my subset. Okay? So the 0 vector, the set consisting of only the 0 vector, is a subspace. And it's a special subspace. We call it the 0 subspace of Rn. Okay, so now we're going to look at another one. We're going to let S be the span of two vectors. And we want to show that S is a subspace of R3. So first off, remember what a span is. The span is all the linear combinations of the vectors in there. So if I have a vector in here, so if u is some vector in my set, then what does u look like? Well, everything in my set is a linear combination of those two vectors. So u is equal to some number times 2, 1, minus 1, plus a second number times 1, minus 1, 2. That's what u looks like. By definition, anything in S is in the span. So it has to look like this. And now let's take a second vector. So a second vector v in S, then v is also equal to some number times 2, 1, minus 1, plus some second number times 1, minus 1, 2. Okay? So my two vectors have to look like this. That's where I'm starting from. Now, the three conditions. Is my zero vector in there? What was my zero vector? 0 is equal to 0 times 2, 1, minus 1, plus 0 times 1, minus 1, 2. Well, that is a number times my first vector plus a number times my second vector. So that's equal to 0, 0, 0. So my zero vector is in my span. So the zero vector is in my subset. That one's taken care of. Second one, vector addition. What happens if I add two vectors in my set? So I'm asking, what is u plus v in my set? Well, what's u plus v? U plus v is equal to, well, it's u1 times 2, 1, minus 1, plus u2 times 1, minus 1, 2, plus, that's my u, plus v, which is v1 times 2, 1, minus 1, plus v2 times 1, minus 1, 2. So that's u plus v. So let's rearrange it a little bit. Gather the similar terms, that one and that one. So I get u1 plus v1 times 2, 1, minus 1, plus u2 plus v2 times 1, minus 1, 2. What do I have? I have a number times my first vector plus a number times my second vector. That is what it means to be in the span. So that is in S. So that works. U plus V is in S. Now what about my third condition? My third condition, I have to show whether or not K times U is in S. Well, I know what U looks like, so K times U is equal to K times U1 times, what's my vector again? 2, 1, minus 1, plus U2 times 1, minus 1, 2. Rewrite it a little bit. That is KU1 times 2, 1, minus 1, plus K times U2 times 1, minus 1, 2. Well, what do I have here? I have a number times my first vector plus a number times my first vector. That is in the span. That's the definition of being in the span. So the third condition holds. So S is a subspace. It satisfies all three of those conditions. It is a subspace. But notice what we have. I gave you two vectors and said, here, I want to look at the span of these vectors, and is it a subspace? Well, my equation showed that the span is a subspace. That leads to this theorem. The span of a finite, non-empty subset of Rn is a subspace of Rn. Okay? So, if you are ever looking at the span of a number of vectors, it is automatically a subspace. You don't have to go back and check all three conditions. By using this theorem, it kind of gives you a shortcut. So for example, if W is this, it's all these vectors in R3, where A and B are scalars. But notice how they're put together. So, take any vector in R3, or in W. So, if U is contained in W, so if it's a vector in this set, then U is equal to 3A plus 2B, A minus B, A plus 3B, for some AB scalars. Well, if it's equal to that, I can rewrite this a little bit. I can pull out the A and the B. I can say that U is equal to A of 3, 1, 1 plus B times 2 minus 1, 3. So it's any number times this vector plus any number times the second vector. Well, that is exactly a span. So that is in the span of those two vectors, 3, 1, 1, and 2 minus 1, 3. So W is equal to the span of those two vectors. And then, by theorem 4.1, W is a subspace. So in this case, all I had to do was show that it was a span of a collection of vectors, and because it is the span, it is automatically a subspace according to the theorem. Okay? So it's another way of showing something is a subspace, if you can show that it is the span of a set of vectors. But now, what does this span mean? Or a subspace? What does a subspace mean? Well, for example, let's take R2. So R2 are your two-dimensional vectors. There are only 3 types of subspaces of R2. There's the zero subspace, which we already looked at. There is any line through the origin. So if you picture your origin, or your plane, and you have 2 vectors on a line, any line running through there. So you have 2 vectors, you add them together, what do you get? You get another vector on that same line. What happens if you multiply it by a scalar? You get another vector on that same line. So any line through the origin is a subspace. All of the vectors on that line, taken together, they form a subspace. The third type is R2. And R2 is simply the span of any 2 vectors, U and V, that are not parallel. Okay? So, there are only 3 types of subspaces in R2. What about R3? Well, in R3, it's similar, but there's only 4 types of subspaces. We again have the zero subspace. We have any line. We have any plane through the origin. And any plane through the origin is the span of any 2 vectors not parallel. Okay? So any 2 vectors form a plane. And then we have R3, the entirety of the space. So in R3 there are only 4 types of subspaces. Okay. Now remember, we had talked about the null space of a matrix. And we had talked about the null space of the matrix being the set of solutions to AX equals 0 and is denoted by null of A. So let's take a look at a null space, and we'll look at an example. Show me the null space of this matrix. So the null space of this matrix, it's all the solutions to AX equals 0. So it's all the solutions to 1, 2, 1, 1, 2, minus 1, 3, times x1, x2, x3, equals 0, 0. So it's all the vectors x1, x2, x3 that satisfy this equation. So how do we solve this? By putting in an augmented form and solving. 1, 2, minus 1, 3 is 0, 0. That's what we've been doing for weeks now. And to solve it, go through our row reductions. So row 1 minus 2 row 2 is the new row 2. What do we get? 2, 1, minus 1, 0. 0, minus 3, minus 7, and 0. And for my next step, I'm going to do 3 row 1 plus row 2 is the new row 1. So I get 6, 0, 3 minus 7 is minus 10, and 0. And 0 minus 3 minus 7, 0. And finally, I'm going to put it totally in row reduced echelon form. So I get 1, 0, minus 10 over 6, which is equal to minus 5 over 3, and 0. And on the bottom row, 0, 1, 7 over 3, and 0. So I did 1/6 row 1 is my new row 1, and minus 1/3 row 2 is my new row 2. So I did those two together. So now I have this. What do I now? I'm looking for my null space. So I'm looking for all the solutions that come out of this. So what do I have here? I'm going to copy this onto the next page. I have 1, 0, 0, 1. Minus 5 over 3 and 7 over 3. And 0, 0. So here's what I have in row reduced echelon form. What does this tell me? Well, my equations are x1 minus 5 over 3 x3 equals 0. x2 plus 7 over 3 x3 equals 0. And x3 is my free variable. So I take those and convert them again. I get x1 equals 5 over 3 x3. I have x2 is equal to negative 7 over 3 x3. And x3 equals x3. Put it in general form or in vector form. I have x1, x2, and x3 is equal to, well, there's no constants here, so my free variable times 5 over 3, negative 7 over 3, and 1. Okay? So there is my null space. Every possible vector that multiplied by that matrix becomes 0 is described by this. But what is this? This is a number times a vector. Well, that is exactly a span. So it's the span of 5 over 3 minus 7 over 3 and 1. My theorem says that if what I'm looking at is a span of a set of vectors, it is a subspace. This is a span. So by theorem 4.1, it is a subspace. So the null space is a subspace. And that is my null space. Here's another space. A column space. The span of the columns of a matrix is called the column space of A. We call it by COL, col of A. So here's an example. Show that the column space of this is R2. Well, this is my same matrix. So 2, 1, 1, 2, minus 1, 3. And I just saw that when I row reduce this, I get 1, what do I get? 1, 0, minus 5 over 3. 0, 1, 7 over 3. So when I do my row reduction, I got that. Well, now, what's my rank? So this was A. My rank of A is equal to 2, and that's equal to the number of columns of A. So that means, from what we saw before, from the last few classes, this means that the column space of A is equal to R2. Okay? And this is going back to all the properties that we saw before. If we have the rank equal to the number, sorry, I put the number of columns, that should be the number of rows. If we have the rank equal to the number of rows of A, then that means that the column space is all of R2. The span of the columns is equal to all of R2. Okay. And the column space of A is, by definition, the span of 2, 1, 1, 2, minus 1, 3. Okay? So that's the column space. It's all of the things you can build out of the columns, which we've seen before. We're just calling it, the first time we've called it a column space. But it is a span, so it is a subspace. So now consider a linear transformation. So we've talked a lot about how linear transformations are really just matrix multiplications in disguise. So let's look at this linear transformation. And this time I'm going to ask for the generating set for the range of t. So you remember what the range is. The range is all of the possible things that you can get from this transformation. So you put in all the possible 4-dimensional vectors here, and take a look at all the 3-dimensional vectors that come out the other end, and that's called the range. So, what is it? Well, in this case, the range of t is all of the vectors of this form. So the range of t is all vectors x1 minus x2, x2 plus x4, x1 minus x3 minus x4. Well, let's rewrite this a little bit. Well, this is equal to, take out all of the variables. x1 times 1, 0, 1 plus x2 times negative 1, 1, 0 plus x3 times 0, 0, minus 1 plus x4 times 0, 1, negative 1. That's the range. It's all of the vectors you can build. It's anything that you can build from those vectors. So it's equal to the span of those vectors. 1, 0, 1, negative 1, 1, 0, 0, 0, negative 1, and 0, 1, negative 1. So since it's a span, that means it's a subspace. Okay, that's using the same theorem that we had earlier, same idea. But now we're looking for the generating set. Well, if something is equal to a span, the generating set is just equal to those vectors. So the generating set of the range of t is equal to these same 4 vectors. 1, 0, 1, negative 1, 1, 0, 0, 0, negative 1, 0, 1, negative 1. That is a generating set. So it's the vectors that you can use to build it. Okay, so that answers the question, but let's look at this a little bit more. But t of x1, x2, x3, x4, you remember, was equal to x1 minus x2, x2 plus x4, and x1 minus x3 minus x4. So what's its matrix? So its standard matrix is, if you remember how to get the standard matrix, it's 1, 0, 1, minus 1, 1, 0, 0, 0, minus 1, 0, 1, minus 1. So our generating set is that. Our standard matrix is that. And notice that the generating set is just the columns of our matrix. So the range of T is the column space of the standard matrix for that transformation. So it's everything you can build out of the columns, and the generating set is just the columns of the matrix, or a generating set is just the columns of the matrix. So that's the connection between linear transformations and the subspace column space of T. So now let's take the same linear transformation that we just used, and I'm going to ask about the null space of T. What is a generating set for the null space of T? Remember, the null space of T is a set of all vectors where T of V is equal to 0. So we already saw, or we know what the vector or the standard matrix is for T. So we're looking for all of the vectors that 1, 0, 1, minus 1, 1, 0, 0, 0, minus 1, and 0, 1, minus 1, times x1, x2, x3, x4 equals 0, 0, 0. So again, we're trying to solve this system of linear equations, and all of the things that turn into 0, that's my null space. So how do we do this? Back to our augmented matrix. So create our augmented matrix: 1, 0, 1, minus 1, 1, 0, 0, 0, minus 1, 0, 1, minus 1, augmented with 0, 0, 0, and start row reducing. So row 1 minus row 3 is my new row 3. I get 1 minus 1, 0, 0, 0, and 0, 1, 0, 1, 0, and 0 minus 1, 1, 1, 0. That's my first step. Now for my second one, I am going to take row 1 plus row 2 is my new row 1. I get 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, and 0 minus 1, 1, 1, 0. And finally, I am going to take row 2 plus row 3 is my new row 3. Again, just doing my standard row reductions. 1, 0, 0, 1, 0. And my second row stays the same. And I get 0, 0, 1, 2, 0. I'm now in row reduced echelon form. So let's solve this out. I can see by looking at it that x4 is going to be a free variable. Everything else is a basic variable. So I have x1 plus x4 equals 0. x2 plus x4 equals 0. x3 plus 2x4 equals 0. And my free variable x4 equals x4. Rewrite these equations. I get x1 equals negative x4. x2 equals negative x4. x3 equals equals negative 2x4, and x4 equals x4. So now my null space is all the equations, or all the vectors, x1, x2, x3, and x4 that are equal to my one free variable, x4, times negative 1, negative 1, negative 2, and 1. So that means that my null space of my transformation is equal to the span of negative 1, negative 1, negative 2, and 1, and that is my null space. Okay, so again, my null space is the span of a set of variables, or a set of vectors. So, in summary, subspaces and linear transformations. The range of a linear transformation is the same as the column space of its standard matrix. Okay, so the column space of a standard matrix is the range. It's all of the possible things that you can build, and it is a subspace. It satisfies those three conditions we gave earlier. Secondly, the null space of a linear transformation is the null space of its standard matrix. Okay, so, and again, it is a subspace. Finally, here are the suggested practice problems. What we did today was section 4.1 from the book. Here's a number of problems that you can look at that will give you a good overview and practice with these topics. Thank you for listening.